Hello everyone, good afternoon. This is live session 11 of the course Sustainable Power Generation Systems, being conducted by NPTEL. This course is taught by Professor Pankaj Kalika, Associate Professor in IIT Guwahati. I am Rohit. I will be taking this live session. This is my profile. So the teaching methodology will be same. Every Tuesday from 7 to 9 p.m. we meet. Then we discuss the topics taught in the weekly lectures so that a recap can you can revisit the different topics which were taught. And apart from that, we'll have doubts clearing. Like if you have any doubts or anything which you want to ask, so please feel free to ask. You can ask your question directly by raising your hand or unmuting your mic, or I will suggest write it in the chat box because sometimes when I teach, then the screen is not visible to me. So I suggest you to write in the chat box that is here in the Google Meet, and then we can in between I will pause and see the question and answer. Also, one-to-one interaction with the students also happens. So if you have any query, please feel free to ask. So discussion forum is also there. So any questions which you think can benefit a bit, larger audience, so you can put it on the discussion forum also. So that is also okay. Okay. Okay, the topic is very interesting. So we'll be basically studying the different storage systems. So energy storage systems are basically systems, as the name says, systems which store energy. But why do we need energy storage? Is it kind of feasible, or is it kind of practical, or is it a necessity to store the energy? So yeah, if you see the demand supply curve basically, so if this is the supply remains constant. So if you see a coal power plant, so coal power plant has steam turbines and everything. So basically if it has a capacity of 250 megawatts, so let's say some losses are there and 240 megawatts are getting generated, so it gets generated at a constant pace, so constant supply is there of 240 megawatts. But what happens sometimes, in the morning hours we generally have a less activity, so demand is very less. Then as the people wake up, then demands goes up, and then in the afternoon hours we have TV, AC, everything working on, so and then cooking appliances, so demand actually surges, that you can see here in the graph also. Okay, so you can see here in the graph. And then in the evening also the demand is there, and then after evening post night, during night the demand actually goes down. So this is how the energy demand curve actually varies, and because of this we need to have energy storage. Okay, so when there is this supply, let's say 240 megawatt, and the demand is only 120 megawatt or something, so what we do, we store this energy because we can't let this energy go waste. Energy is very precious. It takes a lot of effort to generate. It takes uh, fossil fuels, or you can say resources, to generate energy. Okay, so that is so this is the reason that we store the energy. Okay, and when there is a variation, or there is a surge in demand, then we supply the energy, like you can see here. So here, to storage, the energy will be stored. So how do we store energy? So there are different types of energy storages are there. So that we'll see in the upcoming slides also. So in energy storage system, if you see, let's say electricity is there. So how can you store electricity? The electricity can be stored in batteries, capacitors also it can be stored. So these type of devices are there which stores energy, or you can convert electricity to some other type of form of energy, and then you can store that energy also, like you can do it in case of pumped hydro, so that we will see also in the later slides. So this is good, goes to storage, and this is from storage. So when there is a demand, but when there is a demand of, let's say, 300 megawatts, but supply 240 megawatts, so from the storage, energy storage, this demand is met actually. Okay, so overall, the balance, the demand supply balance is very important when you talk about the energy, and the pricing of the energy actually fluctuates because of this demand supply imbalance. Okay, so this is what it is written here. The demand for electricity varies hourly, daily, and seasonally also. Like in winter season, we have very less demand of electricity because fans, everything are not working. Okay, the supply is constant, and to offset the adverse effect of fluctuating demand. So this is what it is talking about, okay, to ensure the steady output from the existing power plants. So if demand is less than capacity, energy is stored like we see here, and if demand is greater than capacity, then energy is released. Okay, so by releasing we means to fulfill the demand. So if there are any questions regarding this, sir, please describe weak for wind power generation last problem. How to also how to question in the exam. So Mukul, actually, this is for interaction for like energy storage system. So let me see if whether I have the questions also. This. Don't you guys have got the solution of those assignments? Because we generally have access to the previous assignments. So let me check it. So this problem not solution in the assignment solution. Wind power generates last problem. A multi-blade. Not getting the actually question also because I have the previous question. So is the question of this type? This was the question. Mukul, can you unmute and crowd and the radius? I don't know. This is the question. This was the question. Okay, this was the question. So, what is the problem of solving this question? This is an easy question, I think. So, there is for the what is answer is this one is the answer. Okay, so this is from the previous run of this course, not from the current question. So, answer can vary because the data will be different from here at this case. So, this is simple question. You just have to apply solidus is given. Okay, zero point 0.5. So if solidus is given and wind speed is given, you just have to apply the actually what you say the formulas to get the answer. Efficiency of reciprocating transmission efficiency is also given. So lift is given. Okay, the radius of rotor is okay. So if you see, I will tell you if you go to lecture 13 or 14 somewhere at something nearby. So you will get the answer. This type of question are there in the lecture slides also. So if you want, I can solve it for you if you want. Okay, so let me check the lectures because that has it's very old lecture. Let me check the formulas. Okay, so let me solve this question for you. So I got the slides. So here the solidus is given. Okay, so the first thing which you will do, Mukul, if you face any difficulty, I'm solving this question. So if you face any difficulty, please unmute your mic and ask, sir, I'm not getting this. Okay. Okay. So don't worry, these are not very difficult questions. So first thing which you will do when answering this, I was thinking the next question. So maybe it's okay. Answering not same, it's okay, no problem. You don't have to match the answers. Your answer is correct. Okay. I think you can write to the discussion forum also, like answer is not correct. So U infinity, that is design speed is given 22. Okay. So this is given in kilometer per hour. So you convert it into meter per second. Okay. So 22 into kilometer 1000 or 13600. So this comes out to calculate. Yeah, 22,000. This is 6 point. 1 or something meter per second. Okay, and then you have Q value equal to 4.5, that is given. Okay, and the second thing is lift. How much is the lift? Water pump. So water pump is operating. So how much is the lift is given? 8 meter. Okay. Now the second thing is the efficiency of pump is required. So I am writing NP is efficiency of pump. I am writing as a fraction. Okay. This is given, and then NT is given transmission efficiency, that is 0.92, and the number of blades as 16. So don't confuse eta. This is eta, not n, and this is n, number of blades. And then length is given 1.4. So you know pump, the how to calculate the power of the pump. So pump is basically, for calculating the power of the pump, rho G Q into H. This is actually what pump power the pump requires. Okay, but the problem with this is ideal power. There is no losses, no efficiency of pump is 100%, transmission efficiency is 100%, then this will be required. But since there is a transmission efficiency and rotor pump efficiency is given, so you just divide it by 0.62. So did you got this concept, or should I make it understand you easily? Why we are dividing it by 0.62 and 0.92, the multiplication of 0.62 and 92? See, I will make you understand very simply. So what I will say, mm, actually what happens, let's say ki how can okay, in simple terms I will say, let's say there is a box, okay, and this box requires 100 joule of energy to lift, 100 joule of energy to basically do anything or work anything. Okay, but there are some losses also, because efficiency is less, so there will be some losses. So to cater for these losses, let's say overall efficiency is 0.5%. So if I give 100 joule of energy to this box to do the work, the 100 joule will not be transferred, it will only transfer 50 joule, because efficiency is 50 joule. So what I will do, I will divide the 100 by 0.5 and I will give that amount. So I will give 200 joules, 100 joules will be lost, and then 100 joules is directly transferred to the box. So similarly in the pump also. So rho GHQ is the pump power, but because of the efficiency losses, we have to provide some extra power to cater for those losses. Okay. So you can calculate rho GHQ will be 98.1 or something. Okay. Watt, and then divide it by 0.62 and 92. Okay. So you will get the required power. So if I divide 0.98 divided by 0.62 divided by 0.92, that comes out to be around. So the required power will be something around 171.9. Okay. So this is the power pump is required. So this power will be supplied by what? So this power has to be supplied by wind turbine. Okay. Basically, this is the wind turbine. Okay. And there is a pump connected with it, which basically pulls water. So pump is requiring this much energy. So this much energy has to be provided by wind turbine. That is clear. So to provide this much energy, what happens, we have assumed the rotor is delivering maximum CP value. So there was a curve there, I think in the lecture slides. Let me show you, there is a curve. So there is a solidus curve with respect to solidus, and so you can check that curve. Where is it? Okay, so if you look the what you say, the lecture slide, there is a curve there, okay, where CP, this is CP and this is lambda. So, and there is one more curve. So based on that, you get the value. So CP max is 1.5. So maximum CP value is 1.5 for this curve. Okay. So based on that, you get the values of, okay. So CP, this is the for a blade length of, so blade length of 1.4, you get the CP value of 1.5 maximum. So maximum, assuming rotor is delivering maximum CP. Okay. So 1.5, you put the value here 1.5. 1.5, and how much power the pump requires? 171.98 divided by half into rho. So density of air is, how much is the density of air? 1.2, and A is the value that needs to be calculated. Basically, radius of rotor has to be calculated. So if you know the area, you can calculate the radius of rotor, and U infinity cube. So U infinity is basically design speed is 6.11, which we got here. So 6.11 cube. Now from here you can calculate the A value. So A comes out to be around 171.9 divided by 152 divided by 6.11 cube. So this comes out to be around 8.37 or something meter square. Okay. So now you know the area. So pi r square is the area, circular motion. Okay. The wind turbine moves like this. So you know the area. So you know the radius of rotor also. Your radius of circle will be radius of rotor. Rotor will move in a circle. Okay. So 8.37. Now do it. 8.37 divided by 3.14, and now take the square root. 2.6656, 2.6656. 1 point something is coming as answer. Okay, 1.633 or something. So the correct answer here is answer C, 1.633 or something. Okay, 1 point, this comes out to be 1.6327. Okay, the answer is correct, Mukul. Okay. I think You must have taken 1.4, but 1.4 is not the, you have to take the maximum CP value. So for this curve, the maximum CP value is at 1.5. Okay. So, okay. So based on that, you get the, okay. Any other question? How many type of question? See, we don't set the questions. The question is set by professor. So we don't have any idea about this course, how the question is set, how mostly I can say that most of the question will be in same pattern as you have solved the quiz question. So if you have good idea about the quiz question, expect the same pattern question in the exam also. Okay. So don't worry, prepare all the quiz question, go through all the lecture slides. The problem is that the students are not going through the lecture slides. So that is why I am doing a recap also. You guys should have a good understanding about how the questions are actually solved. And then bus based on that you will get the questions in the exam. So don't worry, just focus on the lecture slides, you will get good marks. Okay. Okay, so I think I should continue today's lecture. Okay, this is week 4 now. Okay. So if we see energy storage systems, so there are different types, like primary heat source is there. So primary heat source is basically the primary energy. So electricity is not a primary energy. Electricity is basically the primary energy which are obtained in its natural form from the environment, like heat is a primary energy, coal is a primary energy. So there are two things: electrical storage can be there, heat can be stored as electrical storage, and then it can be stored as a thermal storage. So basically, how do we store it as a electrical storage? So we basically generate electricity, and then we have electromechanical devices or direct storage devices also, like storage batteries are there, flywheel springs, compressed air, pumped hydro is there, superconducting magnets are there. And if we have thermal storage, so to store heat, it is very challenging. Thermal storage, we have three types. One is sensible heat type, like we increase the temperature of something, then like rock pebbles. So if there is a heat, then the temperature of rock pebbles will increase. Then you can use the rock pebbles to get the heat back. On a rock pebble is just an example. Okay, so there are different materials also. Latent heat is one of the forms. So to store a sensible heat, basically you need a large volume of material. Okay, but latent heat can be stored just by phase change. So phase change is heat is quite high. So if you see the sensible heat of something, let's say sensible heat of water, it is something around 4.18 kilojoule or something. But if you see the latent heat of water, that is 335 kilojoule. Okay, so you can see we can store 335 kilojoule as a latent heat, not as a sensible heat. As a sensible heat, we can only store 4.18. Okay, so this is how it is done. And then there are chemical reactions. So you provide heat, that reaction happens, you reverse it, and you get heat back. Exothermic, endothermic concept. So first thing we'll focus on the thermal storage, thermal energy storage. So thermal energy storage is basically first is sensible heat. So we store it in the liquid or solid by increasing the temperature. Sensible heat is basically the heat which goes into increasing the temperature. Then we have latent heat, which basically says that no, we will not increase the temperature, but will convert the phase of the material to store the heat. Just like the ice or water can be converted to vapor, so that heat can be given to water and it can be converted to vapor. And now if you condense vapor back, you will get that heat back. Okay, thermochemical storage is there, so absorption storage is there, chemical storage is there, absorption store. Okay, Now we have different types of sensible storage media, like what can be the different types of materials. So I was saying about rock pebbles. So you can see here rock pebbles. Rock pebbles have very bad specific heat, I will say, very bad. So if you compare it with water, so it's better to store heat in the water itself. But the one thing which is considered in case of storing, so there is a rho Cp. Okay, the density multiplied by specific heat, that is very important for storing heat. So the higher the rho Cp value, the more better is the system. Okay, so if you compare all those different materials here, aluminum, brick, in which heat can be stored, so most of the highest rho Cp value is for water, and water is basically available very freely, very economic also to use water. So heat can be stored in the water itself. So water has 3 times more heat capacity than rock on a volume basis. You can see here. Okay, it means rock requires 3 times more volume than water to store the same amount of sensible heat. So why do we go for some higher amount of volume also? Storage should be a compact size. So there are different criteria which you go through lecture slides. You will study that if you want to use some material as a storage, it has a specific criteria. It should not react. It should not have a very high volume. It should not be very costly. So these are some of the criteria. Okay. Now you solve this question. This is a very important question. I think I've taken it from the lecture slides, and I want you guys to actually try this question. And let's see if you guys can make it. Then we can solve this question itself. Basically, I want you guys to try. The reason is that when you try solve this question, and you get the understanding of the concepts in a better way. So take some time, try to solve this question. Okay, and this is very easy question actually, not a very uh, difficult one or something. So the first thing which you will do, what you will do in the first thing itself? First thing is whatever the values are given, first write them down. So volume of, so first thing is volume of steel container. So let's say this is Vs. So you write it down as a Vs. Problem is that it's very difficult to teach with mouse. 175 meter cube. Okay. Then you write the diameter. So diameter is given 4 meter. Okay. Now you write the pressure. So there will be two pressure. One is maximum and minimum. So these are very much important. Okay. So let's say Px is maximum, Pn is minimum. Okay. And then ambient conditions will be is given. So T ambient is given 20 degrees Celsius. So convert 20 degrees Celsius to Kelvin. So any temperature in solving thermal storage questions, so you have to convert it into Kelvin. So this will be 273 plus 20 equal to 293 Kelvin. And then you have this heat transfer coefficient. So let's say HF value is given 293. Oh, sorry. HF value is given 1.5. Okay. And then there is turnaround efficiency and peaking plant efficiency are given. So you have to use this. Try to do these questions. See if you can make it. If there is any issue, please feel free to. There is, so if there is anything which you want to discuss or any issue is there, please feel free to ask. Okay. So the first thing which you will need here is basically the steam table. So you need to get the values of the specific volume from the steam table. So let's say you have two presses, 20 bar and 2 bar. So you go through the steam tables and check for 20 bars and 2 bars, and for this different temperature values, how much is the VF values is there. So you get the volumetric storage, so volumetric amount, and then you can then estimate the, based on that you can estimate the storage time and storage basically. So a specific volume is required here. So I'm not writing the units. Please assume the standard specific units. Okay. So this is in kilojoule per kg. This is degree Celsius from steam table. So I've given the values from steam table. Okay. So as a subscript, I have taken only those values. Like if there is pressure is 20 bar, so I have taken 20 bar as the subscript. Okay. There are also 20 bar. So you can take it as T1 or T2 also. So just to avoid confusion. Now you got these two values from the steam table. Okay. Now basically you have to determine the average density of water. So VF1 and VF20 and VF2, those two specific volume you know. So you just have to take a average of these specific volume to get the specific density of average density of water, you can say. And then you know the specific heat also. So based on that you can calculate the basically total time constant. Okay. So for energy storage, time constant is a very important term, sir. So calculate that. Okay. And then we'll see the next calculations. Okay, so did you got this question? Okay, let me solve this for you. Now every density, so I'm writing it as a very slow. So every density take half of VFA and VF2, so that comes out to be around 896.43 kg per meter cube. So now if you have the density here with you, average specific heat you know for water 4.3 or something, so for vapor, and then time constant you need to calculate the time constant, so that is basically 4 into, so I'm not using the formula here, basically 4 into a specific average density, sorry, volume into a specific heat 4.35, and then this is kilojoule per kg something, so you have to convert it to joule, so 10 to power 3 upon 4 into uh, that specific heat or something that is given, and then to get it in hour. Okay, so that comes out to be around 700.37 hours. Okay, and then for turnaround efficiency, you know the expression NT I am writing, so don't take it as in total efficiency, turnaround efficiency. So I'm just putting the values in the formula. Okay, so time for storage, so this is 0.94, then you equal to, sorry, this cut 1 minus 212, that is you get from the values minus 20 upon this 212.37 minus 120.35, then 1 minus exponential minus ts upon tau. Okay, so you have to get this value minus ts upon tau, and tau you know from here, so multiply it, this comes out to be around something 0.193 or something. Okay, so multiply it with 700, so you will get a storage time as 13.54 hours. So this was the question. Okay, storage time. Now total energy stored in the accumulator, so try to solve it, see if you can get the total energy stored. Okay, so firstly you will need mass of accumulator, mass of water needed to be. Okay, so after putting the mass you will get the values. So MHF1 minus HF, like a specific enthalpy. So you will get the values in the accumulator, energy stored in the accumulator. So try to do it. Let me erase this and try to do that also. टाइम हो रहा है अभी 8:05। अरे Okay, guys. So did you solve this problem? So story time I calculated. You need to calculate the total energy stored in the accumulators. So for that, what you will do? Oh, let me take the pen. So basically, if you have got this value, so you need to calculate the mass. Let me say total energy stored. So first thing is mass. So for mass, you volume is given. You need to divide it by a specific volume of water, 4.35. Oh, sorry. Specific, specific volume of water. Okay, that is 0.0001176 or something. So that comes out to be around 1.48 into 10 to the power 4 kg. Okay, so this much is the mass of energy store. So now total energy stored will be mass into HF20 minus HF2. Okay, so get multiply this into 908, like you get the value in here, 908 minus 504.5. So 908 minus, so take the exact value, 908.5 minus 504.5. Okay, the calculate how much is the value. So this comes out to be around 166. Okay, 78.4 megawatt hour. This is the energy stored. Now again the question is, next question is, so I think I will not solve this next one. This I will give it to you. Total energy that can be delivered by a peaking turbine. So I think this can be done by you. So basically energy stored, this is basically energy stored, and then multiply it with the turnaround efficiency and efficiency of the peaking plant efficiency. Okay. So this comes out to be around 39. So let me solve if solve this also, then let me solve this also. So question C, 166.78.4 is the energy stored, then multiplied with turnaround efficiency and peaking power plant efficiency. So total 3919.42 megawatt hour. Okay, this is the correct answer. Got it? So this is solved. Okay, so if there is any questions regarding this, let me see if there is any questions from the students. Wait, 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 wait. So if there is any question from the students, okay. So like we solved this question, this very important question, and if there is anything which you want to ask here in this thing, this question, so please feel free to ask. Okay, and okay, so have a look, and if anything, so you can write it in the chat box also if anything which you want to ask, so that I can read in between. Okay. Okay, so let me see if there are any questions from you guys. Okay, so now we'll move to the latent heat storage, which basically uses the phase change material like eutectic salts are one of the examples. Okay, during base load operation, the reactor from source directly to heat the water, and similarly condensate coming out. So this is one of the example of the latent heat storage here. Okay, now different materials, phase change materials for latent heat storage, like in organic we have these type of compounds. Okay, for organic paraffin wax and polyglycol, and organic non-paraffin like different acids and aromatics, naphthalene can be used. Okay, thermochemical storage, like we talked earlier, we have sensible storage, we have latent storage, and then we have thermochemical storage. So basically it depends on the endothermic reaction and exothermic reaction to produce a certain endothermic chemical reaction. The products of the reaction are stored, and the when energy is released, the when you reverse that reaction, the energy is released, basically exothermic. Okay, so these are some of the reactions which can be used for storing the energy. Now another concept is mechanical form of energy storage, like compressed air energy storage. So one of the example which you saw, the compressed air energy storage, like wave energy storage. So we have this containers planted in the sea, and then because of wave uh, the cylinder piston movement was there, and that compresses the air inside. So this is one of the kind of the storage can be which can be used, basically compressed air energy storage. So for that, so these where the compressed air can be stored. So this storage can be done in caverns, different geomorphological structures can be used. Okay, so and then this compressed air can be run through a gas turbine to produce power. Okay, this is one of the numericals. So in because there is paucity of time also, so I won't be able to solve this numerical. So I leave it to you guys because this is simple numerical. You just have to put the formula and get the answer. Then pumped hydro storage, because most of the energy storage devices which you will see in real world implementation, pumped hydro storage has a good proportion like 70% or something. So basically what you do, you make upper reservoir, then there is a lower reservoir. So whatever water is used to produce electricity, then this water is basically stored in lower reservoir and then pumped back when there is lower demand of power. So basically when there is excess power, you supply it to the grid, and then there is lower demand from the grid, you use this power to store this water that to upper reservoir again. Okay, so this is how it is done, pumped hydro storage. So it's a very simple concept but very economical and feasible concept, I can say, rather than economical. Pumped hydro storage basically uses the potential energy, and basically this is what it is done. So H is basically a static head, H1 is the losses during the flow. So pumping power is Q rho G QH, and efficiency of pumping has to be divided, and generating power is this. Okay. Then we have this flywheel energy storage. So flywheel energy storage is basically the perfect example is in the IC engines. So we have a flywheel. Generally, when truck is open, in IC engines, what happened? The energy is actually pushed at one time. So in one cycle. So there are four cycles are there, but energy generated in one cycle. So a flywheel is there. Basically, flywheel stores that energy, and when energy not generated in the other three cycles, the flywheel actually supplies the energy. So it is that kind of, basically it can be clubbed with different devices, provide the energy like you can see here in rotor generator systems. Then we have hybrid energy storage, and a lot of work is going on, basically because we are now focusing on hybrid systems like wind turbine and solar PV combined. So we just can't have a single type of storage, we need to have a hybrid type of storage. So this is what basically we club different type of like like one type I can say, let's say this is pumped hydro, and then power is produced, and the solar PV can be used to provide the pump power to the pump, and then again, so earlier the power was provided from the power what was generated, but in hybrid storage it can be provided through wind energy or solar energy, so that can be used. Okay. Now, electrochemical energy storage. So this is also one of the kind of storage. So electrochemical energy storage based on the principle of storing energy in chemical reaction. So one of the example is battery. So battery is not just one of the examples. So there are flow batteries also. Like I will show you in picture. So batteries can be lead acid type, nickel, cadmium, sodium, sulfur, lithium ion is very talk of the town, and then zinc, carbon. So a lot of sodium sulfur is also being explored very expeditiously. Flow batteries are there, basically redox battery and hybrid flow batteries. So this is one of the kind of flow batteries. So in simple small batteries, everything is stored in a packed. In flow batteries, we have a negative electrolyte solution, positive electrolyte solution, and there are big containers. So the chemical flows generated and then they stored back. So this is how the flow batteries basically work. And this is the maturity of different energy storage technology. So this is a very important graph. So I leave you guys with this graph for 1 or 2 minutes, so you guys can actually have a look and see how the energy storage systems are actually in different phases of implementation. And this is one of the very important graph, I would say: capital requirement into technology risk and different stages of deployment. Then we move to the quiz questions, comparative analysis. Yeah. So these two slides are important, and then we move to the quiz questions. So most of the quiz questions are very easy. So I guess you guys will be able to solve it very easily. Okay, so if you see the energy storage technologies, basically the kind of capital requirement. So most of the capital requirements will be in flow batteries and risk is also high there. Similarly, in lithium ion batteries, thermochemical storage have low capital requirement, but they are in research and development phase, similar for hydro. These are in commercial stage, like pumped hydropower, split storage, cold water storage, underground thermal energy storage. So these are actually in various demonstration and deployment phase. Now, if we compare the efficiency and power rate and service life, so pumped hydro storage wins here because it has efficiency power rate at very high, like 1000 megawatts. Service life is very high. Similarly, for flywheels, transmission and distribution, we can have flywheels. Okay, compressed air energy storage. So these are the different things. Okay, now moving to the quiz questions. So if there is anything which you want to ask from the questions, let me see if there are any questions from the. Okay, so Kurs has actually solved that question, I think. Was it the same this airflow question, Kurs? Okay, I think that is the correct answer or something. So yeah, okay. So if there is anything which you want to discuss, because I will give you guys some time so that if there is anything which you want, then I will move to the quiz questions. So quiz questions are much easier. You can easily solve these questions. Okay, so Kurs is actually saying. Okay, so the first question is the most important criteria for selecting sensible heat storage is. Okay, so the most important criteria is basically volumetric heat capacity. Okay, rho Cp. This is very important. Steam accumulators are employed. So what is the use of steam accumulators? So basically when you excess boiler steam is there, so uh, when plant demand is very less, so that can be actually accumulated. So to inject the excess boiler steam to raise the accumulator pressure released when steam plant demand rises. Okay. In case of thermochemical storage, thermal energy storage is done by. So in case of thermochemical storage, thermal energy storage is basically done by exothermic reaction of different reactants. Okay. Thermal turnaround efficiency of sensible heat storage of power plant depends on. So there is turnaround efficiency which we discussed. So it is basically depends on the overall heat transfer coefficient of the accumulator. Now this question is there. A single stage reciprocator takes 1 meter cube of air per minute at this pressure and temperature to deliver 6.5 bar. Assuming the law of compression at this delivery temperature in degrees Celsius as. So solve this question. Let me see if you guys get the correct answer here. So if I write the formula which is basically required by you guys, so T2 equal to T1 into P2 upon P1 and then n minus 1 upon n. So where do you get the n value? N is basically here. PV to power n is constant. So you get the n values. You just put. Now the precaution which you have to take here is put the everything values in Kelvin, not Celsius. Okay. So this is something around 290. Okay. And then 6.5 upon 1.013 1.35 minus 1 upon 1.35. This comes out to be around the calculator 196.8. Okay, so 196.8 is B. B is the correct answer. Okay, now calculate this. Calculate the power in megawatt generated by pumped hydro system. Okay, reservoir height is there, reservoir height is there, volumetric rate of flow is also given, hydraulic turbine efficiency is also given. So this is very simple question. Okay, you know the power of the pump, so rho g hq, and then hydraulic efficiency is given. So multiply it with the power of the pump. Okay, so rho is 1000, this is the flow rate, G is 9.81, H is given 100 meter. Okay, and then efficiency is given 0.8. Everything is crystal clear. I think it's 9.8 into 0.8987. So this is the correct answer. Let me check if so a high speed flywheel has a radius of this, mass of this, rotates at this. So formula is I into omega square. I is basically moment of inertia. So mr square is the I. Okay, and omega is basically 2 pi n upon 60. So put the values and get the answer. Let me see if anybody of you. So put the values here. Let me see. Utkarsh has written B and C. Okay. So solve this question also. So I've given half I omega square and see if you can get the answer. Okay, so this comes out to be around. So you put the values there. I will just put this half into m is 50, radius is 3 square into 2 into 3.14, n is 2160. Okay, half I omega square. This has to be square. This comes out to be around 9.86 joule. The electrolyte in sodium S batteries is basically it's a molten salt. The primary chemical reaction that occurs in lead acid battery during discharge is so reduction of lead oxide to lead sulfate to the cathode. So this is the correct answer. The work required for the two-stage compression of air is 400 kg. The mass of air in the tank is 45 kg. The work output of the turbine unit is 320 kg. So everything is given. You just have to calculate the round trip efficiency. Okay, so this is very easy question. You just have to put the values actually. So first thing is you calculate the energy generated, that is 0.85 into zero point 0.8, that is the efficiency given, into 45 is the mass of air in the tank, and then 320 is the work output. Okay, so it comes out to be 9792 kilojoule. Okay, now energy consumed has to be calculated. So work output is 400. Okay, work required, and then the mass is 45, and then the efficiency is 0.85. That comes out to around 21.17 megajoule. Okay, now overall round trip efficiency is basically energy generated by energy consumed. So 9.792 upon 21.17 into 100. Achha, this is 9 point megajoule, so this is not required into 100. This comes out to around 46.24. So the correct answer is answer A. Now this is common data question. Okay, so this is very easy question. You just have to solve it. So let me solve it for you guys also without any delay. And the quantity of PCM meets demand. So storage efficiency is given 0.87. Okay, and 13% more heat to be stored. So required quantity of heat storage will be 10 to the power 3 is basically given. Okay, and 13% more is basically required. Okay, so required is basically 1.13 into this. Okay, so that is 1.13 into 10 to the power 6 kilojoule is to be stored. Now quantity of heat basically 1.13 into 10 to the power 6, and then latent heat is given 178 kilojoule per kg. So correct answer is 6.35 into 10 to the power 3 kg. This is the correct answer, answer B. Okay, and then the last question in diameter of PCM storage vehicle is okay. So density of solid by density of liquid ds upon dl is 1.05. Okay, so density of solid phase change material, which is basically density of solid 1874, that is given into 1.05, that comes out to be around 1967.7. Then volume occupied by phase change material is basically mass upon density. So mass you calculated in the previous 6.35 into 3 10 to the power 3, and then you divide it by density. So that comes out to be around 3.23 meter cube. Now volume occupied by tubes is basically 15% of the change material. So that comes out to be around 0.48 meter cube. So total volume will be this plus this, that is 3.71. So now you got the total volume, and then assume the diameter of the storage is the height of the storage. Okay, so H into A is basically 3.71, and then A is what? Basically pi d square upon 4 diameter. So height, d and h are basically same. So you need the diameter. So d cube pi d cube upon 4 equal to 3.71. So d is something comes out to be around 1.67 meter. Okay. So diameter and height of the storage cylinder, which will be same, equal to 1.67. So with this, I think the interaction session is over. All the quiz question have solved. So if there is anything which you want to ask, so please feel free to ask here. Okay. If there are any questions from you guys, oh sorry, any questions? No questions? Okay. So thank you for attending this live session, and we'll meet again for the final live session on the next Tuesday, and then there will be a summary session on Thursday so that you can attend. We'll actually have a recap of all the things which we have taught actually. Okay. So thank you again for attending this live session.